I want to turn my attention now in this tutorial to another function in CDAS called Collocate. Imagine if we wanted to do some analysis among the various level 2 products that are generated and had downloaded here a granule, excuse me, from 2021 018, which January 18th of the Modus Aqua. So we have the inherent optical properties level 2 product, which has various absorption and backscattering variables, among others. We have the ocean color, which has remote sensing reflectance, various chlorophyll, organic and inorganic concentration variables, and we have the SST, which has the SST variable. It includes the reference SST and some quality variables and so on. Notice also that each one has its own longitude and latitude so that you can work with its own geography. What we want to do, however, is take these rasters from each of the 3 files and combine them into a single file so that we can then work with those pairs or singles of bands or multiple bands. For example, in a band math band operation, we need to combine those into a single file, and that's what Collocate does. So Collocate wants the files to be in the same projection space. I'm going to go ahead and reproject all of these first, and then do the collocation. To save a little time, I've actually already done that. So I'm going to just open the reprojected files that I've previously done, and that's all that these contain is a reprojected version of the original source data. The fact is, I could close those 3 products, Control W, because they're not really needed as we move forward. We now have a reprojected version. So for example, if I look at the chlorophyll image, chlorophyll A, we see that we are in a cylindrical projection in an area, and that the entire pass is included here, so we're probably going to crop that down as well. Next, let's combine these files into one as is. So the thing with the collocate function is that it uses a reference file, and that's sort of the file whose values will just be carried over into the new file. The dependent file, the values will be resampled to those of the reference file, and having the same projection should minimize any resampling required. Okay, so what I'm doing here is I'm going to select, excuse me, the just to be arbitrary here, I'm going to select, excuse me, the ocean color reprojected dim file as my reference file. So that one sort of starting with. It could be any one of the 3. And then I'm going to bring along the SST. So what we're going to get in the combination is a file with all of the ocean color variables and all of the SST variables. Okay, so we need to give it a name. I'm going to carry some of the original file name, 1935 2021, sorry, 2021 018 1935 And we're going to call this the dot OC underscore SST. Well, let's carry on the fact that it's reprojected, so I'll just put a big R there, underscore OC underscore SST. Could be any name, but this tells me it's reprojected, ocean color, and SST. I give it an output folder, which is where I'm working. Now, down here, it's going to output the bands from this file with a name appended with a name of this form. So it's using sort of the original name as a placeholder, and then appending underscore R for reference file and underscore D for dependent file, so that, for example, latitude in each of the files does not conflict with each other. What I'm going to do is I'm going to change these names to underscore OC and underscore SST. Okay, so that the OC variables will all get underscore OC appended to them in the output file. And all of the variables in the SST file that get carried along into the output file will get underscore SST appended to them. So if I run that, it doesn't take very long. Notice it's writing a file, so it's not only creating it in memory, but it's writing it to the disk. It says it's successfully written a dim file. Okay, so we can close this. Now we have this new file, the .r underscore OC underscore SST. And if we look at the rasters, there are the ocean color rasters, and there are the SST rasters. The ocean color ones all have underscore OC appended to them. The SST all have underscore SST appended to them, which may begin to look a little confusing, but that's okay. We understand that the original was qual underscore SST, and that it came from my SST file into this collocated new file. Okay, so that takes care of these two. We still have to, these two. We still have to come back and pick up the IOP variables. So we simply do another collocation. We pick collocate. Our reference file now becomes this new one that we just made, the .r underscore OCSST. The dependent file that we're going to append to that now is the inherent optical properties. And that's this one here. It's been reprojected, right? So we select that. So now what are we going to call the output? Well, let's append IOP to our file name. So we're going to create a second new file in the same folder. And in this case, we will we can actually get away with the reference file names not having anything appended to them. We kind of already covered that in the previous operation, and we could add underscore IOP here. You might want to use the underscore R and underscore D, or give this some other name, just to make sure there are no conflicts, but I feel confident in this case. I'm going to risk it. So we're going to basically take the dependent bands, or files from the dependent, bands from the dependent file, and tack on this appendix to their name, and run and write a second new file. All right. This file's getting a little big now, which we will take care of shortly, because now we have all of the variables of all three files, some duplicated because there are multiple latitude and longitude variables, and there are some flag variables. They're not really duplicates, but they have similar names and so on. that are building up into this rasters. So we have quite a few rasters now in this final file, b.r underscore oc underscore sst underscore iop. So I'm going to close those and just leave them alone and work on this last one, because now I've got everything together. I've got a bunch of reflectances, chlorophyll. I've got the IOP variables now tacked on, the SST variables in here. So let's trim this down in more ways than one to make it a little bit more manageable to work with. How will we do that? Well, a raster crop. This has been covered in previous tutorials, but it offers us an opportunity to really reduce the size of this file quite a bit, because not only can we spatially crop it, but we can reduce the number of bands that are brought along. So I'm going to kind of approximate the area I'm interested in with this little box and go to the geo coordinates and kind of look at my boundaries and see if I can't come up with some nice round numbers that will probably suit me fine. I'm going to look at these here, 31. Let's maybe go down to 21. Okay, that doesn't cut too much off of the bottom that I'm concerned with. It's a little wide, so what I'm going to do, let's go to, let's say, 82 to 98, that's 16, so let's cut out maybe 82 and a half and bring this back to 97.5, and we now have 15 degrees wide by 10 degrees tall, which is nice and uniformly shaped, if you will. But that's not all we can do. That's going to cut out the size of each raster, but now we can eliminate some of these rasters that perhaps we really don't imagine we are going to need. I've made a mistake. So rather than start over, I'm going to fix this mistake. I'm going to cancel out of that. I was viewing the chlor A, which is from one of these other files, which I should have closed. So Control W, I don't care about saving that. I'm going to Control W, and now you notice that closed the viewing window. So I fell into that trap. Let's open a band from this file. Let's look at our SST. Okay. Now let's do our raster crop. This is the dependence this function has. You have to be viewing a band in the file that you want to crop. And so I go back to my geo coordinates. I had decided on 31 degrees north by 21 degrees south, and I had decided on minus 97.5 west and minus 82.5 east. And now I should see all of my bands. This was the tip-off. I wasn't seeing all of these bands that I've put together. You have an option here to simply select none and add the ones you want, or if you think the majority of them you'll keep, you can select all and then just uncheck the ones you don't want. So I'm going to eliminate the latitude and longitude that came along from these and just keep the ones from the ocean color. It shouldn't matter regardless. I'm going to keep my level 2 flags. I'm not going to worry about fluorescent line height or photosynthetically available radiation. I'll keep the SST. I'll keep the SST flags, the reference SST. I'll keep the quality levels, more flags. I won't bother with this bias or standard deviation variable. I'll keep all the absorptions, all the backscatterings. I don't, this is all just contrived. I'm going to eliminate some of these. They might be useful. They might not for the science that one wants to do. But those are the ones I'm going to keep. and I simply click OK. Now this, remember, crop creates an in-memory unwritten file. So what I'm going to do, it's created this underscore subset, is I'm going to save as right away, and I'm going to mimic that file name, OC underscore SST underscore IOP underscore, and I'll just use a capital S for the subset, and save that. Okay, so now I have a disk file written out that I can begin to do as much science and analysis on as I want. It's only got these variables in it, and I can begin viewing them. The 448 in RRS, the 448 in absorption, and the 448 in backscatter. I can, if it's useful, perhaps tile those vertically and look at them for whatever I might want to look at. Okay. This offers other functionality that I'll go ahead and include here, and one of which is the scatter plot. You can now do a sort of correlative plot of two bands. So let me click that and pull up this user interface very quickly. What this lets you do is pick from the available bands a band to be the x-axis and a band to be the y-axis. So across the bottom, I don't know, I'll look at SST, and up the y-axis maybe I'll find one of the chlorophyll variables. I have no idea if it's meaningful to plot them, but you simply select them, leave this auto min max, and refresh with this tool here, this button here, and what you get is one of these plots. Now right away I can see it's kind of squeezed down. Maybe this is useful information. I can go into my y-axis and change the max. Maybe I'll just cut it off at like 20, change that, and then refresh the plot and kind of expand it. What this has done is colorize the number of pixels that occur. It creates 512 bins, as I understand it, to put pixel values in, and then it colors based on, there are many more pixels at 22, let's say 20 to 27 degrees under 1 milligram per cubic meter, or sorry, meter to the -3 cubic centimeter. In the two plots, there are many more than all of the rest of these. These are just sort of so this is just a tool that can be used if you know of meaningful science to apply, in which you can plot one band against another band to see how they correlate. And you can't do that between an SST and a chlorophyll variable until they're in the same file in CDAS, and that's why we did the Collocate to begin with. So I'll wrap it up there, and hopefully that's useful and you can do some real science with it.